Tech. So I'm requesting Think Again Lab to start the session.
Good afternoon, everyone. Thank you so much, ma'am, for this opportunity. And we are very enthusiastic for today's session because it's not about any dull subject. It's about rocket science. So it's sometimes we say that learn web design. It's not a rocket science. Learn this. That's not a rocket science. But today it's seriously a rocket science workshop where we are going to learn about rockets, space, spacecraft, orbiters, different space networks, and all those kind of stuff. But the thing is, I want to clarify one thing first, that space is a very huge thing, right? And it's not possible for any human being, even he is the best scientist in this world, to teach you rocket science in 3 hours. So what we're trying to focus, we're trying to get you introduced with rocket science, space tech, different. I will provide different resources that will really help you to foster your interest towards space. You can get informations, you can see images, videos, different apps from NASA. So I will introduce with all those things. I will explain different kind of spacecraft and their parts and how they work and all those kind of stuff. And on the other hand, Anirban will start with the rocket science, how rocket really works, uh, how actually rockets go to the space, and we will actually build a rocket in a simulator and fly it. And that's a wonderful simulator because that simulator actually allows us to build real kind of rockets. How they have all the components that's are getting used in space nowadays, and we can actually use those components to build our spacecraft. Like recently we are building a spacecraft that will just bring a rover to Mars, right? And all this in another simulation. Now see how can a simulation be effective? They are actually a real life simulator. What is a real life simulator? If you are doing something wrong, then that will be reflected on your simulations. So if you couldn't build a proper rocket, that will just go and dump into the ocean, or just lose its path and blast off in the way, right? Or yes, suppose sometimes in the initial days, what we have done, so we build rockets and put the rocket into the launch pad, and somehow forgetfully we have just closed the hatches and didn't start the rocket, so it just fell down and broke over there, right? So it's a fantastic kind of simulator where you can really see all the components of a rocket, like propulsion engines, the nose cone, different kind of heat shields, and all those kind of stuff, right? So we are going to build a very simple rocket, but interestingly, we are going to give you a demonstration of the rocket we are actually building to send it to the Mars in the simulator, and explain different parts of it, right? So let's start with the absolutely beginning thing. What is rocket science? Different parts of rockets in a theoretical way. Then we will get into the practical way, and in between I will come and I will just actually ask you questions in real time, right? Because this is rocket science and it's not from your books. So all the questions I'm going to ask, that is from today's presentation and your presence of mind, right? So be very careful, understand everything, and if you couldn't understand anything, just come to the comment box, ask questions. I am there to answer. Anirban is there to answer, right? So let's start with the rocket science, and with no more delay, Anirban, please start.
Am I audible?
Yes.
Yeah.
Okay. So let's begin. So uh, yeah. So basically, what we are going to be studying today is rocket science, right? So whenever in India there is a saying that it's not rocket science. So whenever we are trying to do something difficult, people tell us it's not rocket science. So because rocket science is always associated with the highest level of difficulty. So today let's understand what is rocket science, like in a basic concepts, and then in the end of this class I am gonna ask you that if this saying this is not rocket science is true, if it is really difficult or it is understandable. So without any further ado, let's begin. So what is a rocket? So basically a rocket has a very simple principle. A rocket basically converts chemical energy into a force. So basically, how does it do that? Via combustion. So the engines that we use in our cars use the same technology, internal combustion, right? But where in our car we are doing a passive way of translation, where we are combusting some chambers and then spinning a shaft, and then the power is getting supplied to the wheel. A rocket deals with this combustion in a very direct manner. So what does it happen? So basically you put the fuel in there, you burn it through the nozzle in the bottom, it creates a pressure downwards, and due to the Newton's third law, everybody of us know that every action has an equal and opposite reaction. Since the force is down, the rocket goes up, like so. So basically, this is the textbook definition of rocket that I have written down. But like, see, it's very simple. A rocket is a device that produces force downwards to propel itself upwards. That's all there is to it. So now, these things, right? These things, these fireworks, we also call them rockets, right? And we burn a lot of them during Diwali. So let's see how this rocket operates. This is very important. Please pay attention to this video, because in the next slide, I'm going to ask you a comparison that how is it different from an actual rocket. So please watch carefully. Okay. So the person is writing the rocket, and there it goes. So this is basically a very common sight, right? During the puja seasons and yeah. And now we are gonna watch a real rocket. So this is a SpaceX Falcon, one of the delivery ships to ISS. So let's watch how this thing does. So there is a countdown, there is a liftoff, and there it goes. So can any of you guys tell me that what was the difference? So how is this big rocket different from that small rocket? What is the basic difference? What if we made a big rocket out of those small Diwali rockets and we launched them? What will be the difference? Can you all tell me in the chat? Anyone got any ideas? It has escape velocity. Not really. Look, if we like put a bunch of small Diwali rockets, that will also produce escape velocity. But the thing is direction. So basically, what is happening here is when we are putting a thrust in a direction, okay, there are some other moments of force as well. So there is a technique that has been developed in this rocket science industry. It's called thrust vectoring. We will learn about that a little later in this course only. So this thrust vectoring allows the rocket to stay straight up on its way. Okay. While in the Diwali rocket, there is no thrust vectoring. So as we can see, this rocket went straight up in the predefined trajectory. While in the case of this Diwali rocket, as we can see that there is no trajectory, there is nothing called a trajectory. It can go in any random XYZ direction, right? You just light the fuse and then you don't have any absolute control over the rocket. So that is the main factor in building a rocket, that is control. You can get as much power from an engine as you want, but if you don't have the control, there is no use of the power, right? So see, it went in a random XYZ direction. You have no idea where it's gonna go. You cannot predict if it will go into the outer space or not. So, since I was talking about control, so let's now learn that how does a rocket achieve this control? Okay, so this is how it does it. So this is the parts of a rocket. So there are like different parts of a rocket. These are very simplistic explanation really. So first part is a nose cone. Nose cone is basically the last thing that we will do, because this is the place where the payloads are and the crew etc. sits. Like this is the part where there is cargo essentially. Next up is the fuel tank. Okay, so let's get to it. See, these are the fuel tanks of the rocket. Okay, so this is where the fuel is stored. So throughout this session, I am going to be giving you examples of cars, because we see vehicles on the road, right? But we don't see rocket launches live every single day. So that is why I am going to be giving examples of cars so that it's relatable. So let's compare this fuel tank to the fuel tank of a car, right? So it has like a valve system that controls the amount of fuel that goes into the engine, like a car. It has the same thing, except the fact that the material of the outer shell. While your car experiences maximum temperatures of like maybe 110, 120 degree Fahrenheit, these things, while escaping the atmosphere of the Earth at terminal velocity, experience much higher rate of friction and temperature. That's why these specific tanks are made with ceramic composites, not metal, not anything else, ceramic composites, because those things are excellent in absorbing temperatures without increasing the internal temperature of the actual tank. So this is the main difference between your car tank and this rocket tank, the material of building. And of course, it has to be made pointy, as you can see, to be aerodynamic. Anything pointed is aerodynamic. Why? That we will also be learning in this session. So now, since we are talking about the tanks, type of fuel comes into mind, right? That okay, my car has a fuel tank, rocket has a fuel tank. My car runs on petrol. What does this rocket running on? So this is where the fuel type of fuel comes in. Okay. So like your car, that can be either petrol or diesel. Rocket fuel also can be categorized broadly into two categories. One is solid fuel, one is liquid fuel. So this is basically a solid fuel booster. Okay. So solid fuel is essentially powder. Like there is like a mixture of flammable powder and a buffer that controls the rate of combustion, right? So that it does not explode. So this is the main difference between a bomb and a rocket engine, right? So both of them have combustible material that explodes, but one of them explodes in a random reaction and causes destruction, but the other one drives a vehicle. So this is the difference, that is the buffer material. If you don't add the buffer material, your rocket essentially becomes a bomb, because the rate of burning of the fuel will be too high and it will burn everything at once, producing a big amount of energy that the body of the rocket won't be able to hold. So this basically this white line you see in the middle right there, that is the buffer material, and this
So I
like,
have a question to the audience. Like, from your real life, can you give us example that why we are using liquid fuel in case of rocket, not solid fuel? What is the case? How from real life, how we can actually understand very simple example that have we ever dealt with liquid fuel and solid fuel in same purpose, and we can understand how these two things are different, and how we can actually why we actually use liquid fuel in rocket science. Any idea? Anybody? You can comment down your answers. And today it's absolutely interactive session. I have to ask questions and you have to help in combustion. Solid fuel also helps in combustion.
yeah,
I'm always
yeah.
confused about what. Okay, liquid burns easily than solid. It burns better. No sir, no idea. Help in combustion. Okay. Okay, fine. Okay. So
No, they're close. Like it's about burning, but it's not like
the
how it
thing
burns.
is, let's take a simple example from your life. Everybody we have
Yeah,
dealt with solid fuel and liquid fuel, and the example is matchbox and a lighter, right? So in case of matchstick, you can burn a matchstick, you can get a light out of it, a heat out of it. Those are energies as well, right? In very small amount, right? But the difference is, in case of lighter, you are having a controlling switch. You can make the flame bigger, smaller, you can control the power, right? So this gas, this liquid burns in a controlled environment. You can actually control the environment, because when it's a liquid fuel, you can just stop the supply of the fuel and the combustion will be stopped, or it can be increased or can be decreased in the same way. It's controlling a valve, right? It's a simple like a tap of a water, right? But in case of solid fuel, if it catches the fire or catches the ignite element, whatever the element is, when it start burning, you couldn't stop it until it's just completed burning all over, right? So that's why when you just burn a matchstick, you couldn't reuse it. But in case of lighter, you can reuse it, because you can stop it, you can control it, you can change the intensity of this thing. And that's why, so this is the very simple relevant example from your real life to understand that if we use solid fuel in a rocket, we couldn't control it. But when we are using a liquid fuel, we can actually control its power according to our needs, so that we can reach the escape velocity as well as control the direction of the whole rocket. So that's why we need to use liquid fuel, liquid propulsion fuel for this thing. Liquid fuels generally provide more energy than solid fuels and are easier to control. Exactly. Soil vicious. Thank you so much. Exactly. So this is the reason, right? I hope it is much more easier for each and everybody to understand the thing from a very real life perspective. Anyways, continue.
Okay, so basically, as we have already learned, that liquid fuel can be regulated, it can be controlled, it can be used as a direction of driving, right? So now the question begs, why are we like developing this buffer and stick thing at all? Like, if we don't need it, why are we developing? So basically, a rocket in technical terms is called a launch vehicle, okay, because it launches something, you know, the payload in the nose cone. So it's called a launch vehicle, okay. These solid fuel cells are known as support vehicles, launch support vehicles, okay. So what does it mean? That they support in the launch of the rocket, okay. They don't go all the way to space, but they instead support in the launch of the rocket initially at the ground level, okay. One of the other applications of this solid fuel is missiles. So what is the main difference between a rocket and a missile? A rocket is basically a scientific device, and a missile is basically a military application device, right? So missiles are generally, you know, one switch thing. Once you turn them on, there is no turning off because they will hit the target anyway. So that is why solid fuel is used in missiles as well as support vehicles. So what are support vehicles? We will learn in a few moments. So for now, let's switch to liquid fuel. Right? So now, what is the liquid fuel? So now this is a liquid fuel propellant. Okay. So as you can see, there are two tanks marked by orange and green. So can anybody tell me what are the two tanks? Can anybody tell me in the chat what are the two tanks for? Like liquid fuel, like petrol or diesel, it needs only one tank, right? What is the other tank for? Any ideas? Oxygen. Fantastic. So this is basically called the oxidizer tank, and it basically consists of an oxidizer, which in layman's terms is basically liquid oxygen. Okay. It's liquefied oxygen. So why do we need to carry oxygen? Like we have a lot of oxygen in the air, right? Our car also runs on oxygen from air. So why is there a tank in a rocket where space is extremely valuable? Why is there a tank where we need to carry oxygen separately in a liquid state? Why is that? Okay, there is no oxygen in space. Fantastic answer. So yeah, basically there is no oxygen in space. So as we are reaching the boundaries of Earth, as we are exiting the troposphere, we need to balance this oxidizer with the decreasing amount of oxygen in air. So as it goes upwards, the oxidizer tank switches in, maintaining the level of oxygen inside the tank, inside the combustion pipe, so that the rocket does not stalls and falls down. Okay, so that is basically the main reason why there are like two tanks in this setup, like liquid propellant setup. Okay, so I guess the fuel thing has been cleared out to everyone. So now let's continue. Now we have learned about the liquid and the solid fuel. So this was a slide meant to understand the features of the liquid fuel and the solid fuel, but we have already discussed them. So as you can see, for the liquid fuel, we have high specific thrust because yeah, liquid fuel burns more efficiently because we have oxidizer and stuff. We have restartable. So as we know, we can control and regulate liquid fuel. So it's restartable. We can turn the engine off and then on again as many number of times as we want. And thrust can be controlled. So yeah, we have a regulation, right? So yeah, those are the features. Now for solid fuel, we have high density and compact size. Why? Because you know solids are powder. So a powder can be compressed more than a liquid, right? You can like if we spread out 1 liter of water and spread out 1 liter of something powder, okay, powder substance, the powder will spread in a more area, right? Because it can be compressed to a higher degree. So this is high specific density and compact in size. So basically you can fill up more volume and compress it into a smaller size in a powder
I
situation.
have another question to the audience.
Okay.
that so I am working like a big boss, right? I'm coming to the house and asking questions and all those kind of stuff. Anyways, also teach you certain things regarding the rover and all those kind of stuff. But in the rocket session, I am just behaving like a big boss. Anyways, so like why liquid is taking more space than solid? It's a chemistry and physics question. It's not a rocket science question, because rocket science is not another kind of science. It's amalgamation of all kind of science to do certain thing related to space, right? So why why same amount of liquid is taking more space than, yeah, fantastic for burning. Okay, in intermolecular force of attraction, uh, actually related. You have used one term. I just want another term. It's not force. Force of attraction is the cause, because liquid molecules are much loose. Exactly. And why it's loose? Why it's loose? We already got one part of the term. There is another part of the term. Can you tell me what is the term that is actually making something loose or tight or something like that? Though it's not for van der Waal, uh, not, yeah, van der Waal, but I am asking in a very simple sense, that intermolecular distance, right? So in case of liquid, the intermolecular distance is more than the solid, and that's the reason liquid can be compressed less than solid, right? So it's absolutely simple chemistry we have learned in class 8, 9, 10, and that is getting used in space as well, because we have to understand that whatever we have learned anywhere, that can be used to space, because space is huge. We can use anything, creativity, drawing, whatever you can do. I want to share something over here. So in case of like 2015 or 16, the winner of NASA Space Up Challenge, so it's a international level hackathon. The winner was from a school, and what he drew, what he did, he actually draw a spacesuit, right? And that was selected by NASA as the global winner. Just a drawing, whereas the competitors build drones, robots, so many things. But the thing is, it's not about your domain of expertise. It's about the implementation and impact of the things, right? So that's why space have space for everyone, right? So everyone from any discipline can actually get into space, and I will actually describe all those things in a very brief manner today, that how actually we can sit at home and be a part of NASA, be a part of ISRO, and do several things with them, for them, and several kind of stuff, right? So that's making space more interesting. It's so vast. Any kind of talent can be accumulated within that space, right? That's the thing. Anyways, Honorable, continue.
Okay. So basically, this is a design by the NASA. So this is basically a Mars helicopter design. So never mind that. We'll come back to that later. So now let's get to the other section. Hold on. Okay, so we have learned about fuel, right? So let's learn a bit about the engines. Okay, right. So basically, I didn't include the engine slides because I want to show them the engines to you guys in the simulator. So while using the simulator, I will explain about the different type of engines. I will explain thrust vectoring. I will explain how you can use solid fuel and liquid fuel engines together and stuff like that. Yeah. So now let's focus on the final thing, that is the nose cone. So basically a nose cone is basically the part of the rocket that is usually on the top. So as I mentioned earlier, it's a payload carrying device, basically. Okay. So now, as we all know, that there are different kinds of nose cone, right? Some of them are big, some of them are small, as we see in our own rockets, right? The PSLV, the GSLV, the GSLV Mark II, and then there's the SpaceX, like the Falcon 9, the Falcon 9 Heavy. So all of these different rockets have different types of nose cone. Now, why do you think is that? Like we have a shape, and depending on the shape, we have a function, right? And also, why are the nose cones always pointed? Because as we have seen with our Diwali rockets, like nose, they have a flat, very flat nose cone, right? They virtually have no nose cone, right? So why is that really? So let's first see that. Okay, so basically this is the logic. Okay, so the more curved or pointed you get, the less drag you have. Basically, what is drag? Drag is basically like a more complicated term for friction. Drag is basically the friction that is caused by the air, right? So when you are moving something through the air, if this object is blunt, say I move this thing through the air, right? Like with a flat face. If I move this thing, I will have to put more force, right? But if I move this thing like this in a flat manner, so I will need less force, right? So that is why the aeroplanes, the kites, name anything that fly, they are always pointed, right? Pointed, flat, and light. Because one, if it is pointed, it will have less friction or drag. If it is thin, same thing. It will generate more lift and have less aerodynamic friction. Yeah. Someone already said that in the chat. That's very good, really. If you are paying attention, I'm very happy to say that. And finally, if it is like light, it will obviously have like a easier time getting off the ground. So these are the three things that like factors into most flying objects, rocket included. Weight, shape of the top, where in the direction where it is going, and the aerodynamics, the fins, the thickness of the stuff. So also that is also why a rocket is always a cone, a cylinder. Okay, a rocket is never square, a rocket is never triangle. No, it's always a cone. You know why? Because a circle has no sides. Okay, and a cone is basically a circle in a 3 dimension, right? So a circle has no side, so it will have a similar kind of air friction in all around, and there won't be any points where the air friction is more than the other place. Otherwise, that part will get more friction and it will just bend towards that part, and it will be very hard to control that rocket. Now, these are some of the more explanations of the cones. So these things are the subsonic cones. So these designs are usually used in subsonic vehicles. Subsonic means less than the speed of sound. And these shapes are used in usually supersonic vehicles. So supersonic means more than the speed of sound. And this pattern, if you look carefully, you can find it any number of things in nature. Okay, birds, aeroplanes, even bullets. So if you look at this carefully, I don't know if you guys know about guns and bullets a lot, but this thing usually is like a revolver bullet, like handgun bullet. So this thing goes slow, and this on the other hand is like a shape of a sniper bullet. So that's a marksman thing, and it goes really fast, and it goes really over a 1 kilometer range and stuff like that. So same thing, same pattern appears everywhere, including rocket science. So in rockets as well, if you are making a subsonic rocket is usually one that does not go outside the atmosphere. It goes up, collects some data in the upper atmosphere or something, and comes down via the parachute. So that's a subsonic rocket. And the supersonic rocket is usually the ones that go outside the troposphere, into the orbit, into other planets, and everything. So if you guys really see, I have a vast syllabus to cover, but if you guys think I am going too fast, you guys cannot understand, you are having a problem, you guys just comment it out, I will stop there and there, okay? Explain again. So, whatever I just told right now, right, about the shape and stuff like that, so this is basically like a actual air resistance test in SolidWorks. So SolidWorks is basically a device where you can simulate physics, like the simulator that we are going to use, similar kind of stuff, where you can simulate physics and see the effect of any like gravity, air resistance and stuff on objects. So this is the same thing, just have a look. So this is what I have been telling you guys about, that how the shape affects the resistance. See, as the speed increases, see how the air reacts. See, these fins are producing like the stability, right? Now it goes supersonic. See, as soon as it goes supersonic, that thing vanishes. As soon as the rocket goes supersonic, all the friction comes to the back, and the center of gravity just moves. It just shifts. That is why it is important to like balance out the fins. If you make the fins too big, as soon as it hits supersonic, the fins will have more drag than they can control, and the rocket will just flip. And it will go into the spin, and then it will crash inevitably. Okay, so now this is the function of the nose cone. Now we have known the shape of the nose cone, how it is shaped is supersonic, how it is shaped is subsonic, and now we have to know what is this nose cone for. Like, why is this in the top of a rocket?
So here I came again. So somebody asked previously that I am very much confused about payload. So what is payload? Fantastic question, and that's why we are having a. So we predict the future, and we are having a slide for payloads itself. So in very simpler way, tell me what is a rocket. So we have already learned about rocket. What is a rocket in a very simple way, very simple terms? What is a rocket? What is a rocket? A vehicle defying gravity. A vehicle defying gravity. Fantastic. A delivery vehicle. Rocket is a delivery vehicle, right? Fantastic. Now think that your Uber car is a delivery vehicle. A rocket is the machine that can help us to get rid of gravity. Yeah, it's a more technical, but I am just trying to relate with simple things in your real life so that you can understand that if you book a Uber, you are booking a rocket, right? So it's a vehicle, delivery vehicle. Now, in case of Uber, why you are calling the Uber? So that it can deliver you from one place to another. So Uber is a rocket whose payload is you and the driver. And that's why payload is nothing but the things that needs to be delivered somewhere. It can be a satellite, it can be a rover, it can be human being as astronauts, it can be supplies, it can be anything, right? So the rocket is a delivery vehicle and which is delivering certain substances, and those substances are treated as payloads. As simple as that. So payload is certain things that needs to be delivered in space, and the rocket is the vehicle who is actually delivering it. As simple as that. Fine. So continue.
Okay. So yeah, somebody wrote SpaceX. Yeah, SpaceX is basically the Uber for space. Yeah. So basically, ISRO also does the same thing sometimes, right? So if you guys remember, recently ISRO made a world record by sending 125 satellites in a single GSLV Mark II launch, right? That was like that 125 satellites that they sent together in one rocket. That 125 satellites was the payload for that rocket. So that helps you to understand better with the example. Now the function of this thing. So this is where we discuss the payload, right? Payload can be of two types: organic, inorganic. Inorganic, basically, as the name suggests, is basically anything that is non-living, like satellites, rovers, like hardware for the ISS, International Space Station, and stuff like that. Monitoring balloons, anything you name it. And then there is the organic part. Organic means humans, mostly humans. Then there is also food delivery and water delivery, like essential stuff delivery for the ISS. And sometimes they take animals like cockroaches and ants to ISS as well, International Space Station, for understanding and experimenting at how those organisms react in zero gravity and stuff like that. So these are the organic side of the payload. Now the payload type, if it's organic or inorganic, determines the type of the nose cone. It's very simple. Like if you start sending a robot, or say a robot for example, or satellite, do they need oxygen to breathe? No, right? Do we need atmosphere to protect them while they escape the terminal, while they escape the troposphere at the terminal velocity with extreme heat and friction? No, because they can take it. Just build a titanium body for them. They can take it. But can we take it? No. We will become, literally become like a roasted human or something like that. So we don't really want that happening to our astronauts, right? So when we are sending an organic payload, like humans or anything, a living thing, to make sure that it reaches the outer bounds of Earth into space unharmed, we need to follow like strict safety procedures. Remember, like in 2008, after the Columbia disaster, how NASA got backlashes, like the space shuttle program got literally cancelled for the Columbia disaster afterwards. So basically, that is the cost of like failure in while you are dealing with organic payloads. Okay, so yeah. So this is basically the delivery of. I think you guys, many of you guys would know. Like, can you guys tell me what this is? Like, this is a very known figure. Like, it's a satellite, but it's a very known satellite. Any ideas, guys? And it's also in black and white, so that should give you a clue what this would be. Any ideas? Okay, let me give you a hint. This was a satellite named after an Indian astronomer. Now, anyone? No? Okay. So, has anyone heard about the Aryabhatta satellite? So, this is basically it. This is a launch vehicle for Aryabhatta. One, because there are like many versions, 1, 2, 3, 4. So, this was basically one of the first launches of ISRO. And that's why it's in black and white. Because we still didn't have the capacity to take color photos in space like at that time. Now, this is basically the latest Dragon module of SpaceX. This is like the latest standard capsule for transferring humans to ISS, and this is like the size comparison. So, see, this human, this is my size, right there, and this is the like the capsule where they will go in. Okay, and if you guys have seen the SpaceX launches, any of them, or you have seen any pictures of the astronauts inside the, okay, maybe, hold on, maybe I have the picture, yeah. So see how much the space is crammed inside. Like you'd think like that there would be more space since that thing is so big, but there is so much little space inside. Any idea why? This is because of that titanium shell and all the heat shielding I told you guys about. So the layer is so thick that it takes almost all the space of the capsule. So maybe from outside it's looking this big, but from the inside it is this small because it takes a lot of space to insulate and make sure that these astronauts don't get harmed while they exit the Earth's atmosphere. And we're back to the fuel tanks. So basically that is it for the presentation. Now Arjita will tell you about some of the NASA and ISRO events that we are collaborating with, and then I will load up the software, and then we will jump into the simulator and we will do some experiments. Arjita? You there?
Yeah.
Yeah.
Fantastic. So we now know about the launch vehicles and delivery vehicles, right? Rocket. That's very interesting thing. So after I will go you through a few websites, web apps, and different interesting aspects of NASA, ISRO, and all this kind of stuff. Then we will start with making the rockets and launching it, right? And that's a quite climax point of today's session. So that's for later on part. Otherwise, maybe you can left after that. That's so much interesting thing. Anyway, so let's start with something less interesting, I hope, but I hope that will be very much inspiring for you to get into this space related domains and all those kind of stuff. And most interestingly, that today we are talking about space science, the rocket, and all those kind of stuff. But it's not like you have to be the rocket science engineer only to get into space. Why I'm saying that? Because many people who are space enthusiasts, many students who are space enthusiasts, they just drop their idea of getting into space domain or space technology domain, just because they think that I am not good with maths, I couldn't get into space. I'm not a scientist, I couldn't get into space. I am an artist, how can I get into space? So the thing is, if you are a space enthusiast, there are several pathways through which you can actually get into the space technology domain, and rocket science is one of them. It's not the only way, right? Like we have already done the session of data science, right? So data science is one of the premium domain through which you can actually get into space. Like I showed on that day that if you go to data.nasa.gov, you can actually get a lots of data sets of NASA. If you can use the knowledge of data science by analyzing those data, if you can come up with some patterns that yet not deciphered, then maybe you can join NASA, you can join ISRO, you can help the humanity to achieve certain non-solved problems, right? So that's one way. Another way, that do you need to be a proper engineer having like for data science also you need mathematical strengths and all those kind of stuff? No. If you are a artist, if you are a photographer, if you are a graphics designer, if you are a digital media marketer, in every way, if you have smartness, you can actually align your career towards space. And it's not like every time you have to be got employed by a space agency, because in the world there are very less number of space agencies so far. In coming last few years, few private space agencies are coming up, but mostly it was like in government's domain, and not that much capability to employ all the space enthusiasts in this world. But there are certain subordinate secondary pathways through which you can actually become a space related entrepreneur, space related freelancer. Like in the digital media marketing webinar we are having in the list that you are going to participate, we are going to learn how to become an influencer, how to actually use the power of social media to build a career upon it, right? That you are actually spending, so every day I know all of you must spend like 3 to 4 hours on social media, not at a stretch, but if we just calculate the whole time you're spending on social media, that is 3 to 4 hours. Now on the digital media marketing webinar, we are going to describe that how actually you can spend that 3 to 4 hours and earn money out of it, rather than only wasting your time just scrolling down and engulfing all the negative news and all those kind of stuff. Actually you can use the power of social media to actually earn money, actually make a career out of it as a freelancer or innovator or a researcher, right? So what are the ways through the social media? Why I'm telling this? Because it's an entrepreneurship development camp, right? So it's not about teaching you about the rocket science of space. I must teach you how to actually you can venture out with those knowledges to earn money and create a career out of it, right? And you don't need to be dependent on anybody, not on campusing, not on anybody, that you need to get a job, you need to do something on space and nobody is helping you. You can do it by your own self, right? So you can just study all the NASA websites, all the space agency websites, collect data from there and start creating content. You can become an influencer on the space domain. You can have a Instagram channel, you can have a Facebook page, you can have LinkedIn page. Like on the other day I was saying that when we approach to different kind of influencers for promoting our companies, they charge like 15,000 rupees, 20,000 rupees for a single post. So if you are like space enthusiast, you love to know about space, learn about space, you can start learning about space, and alongside you are actually educating people what you are learning, and you can actually make a career out of it. You can have an Instagram channel, and you can go and like few other Instagram channels and see how they're creating the content, how they're publishing. And if you want that from where I can get the information, I can learn. So today I am going to show you certain places where you can get whatever kind of infos you want, because space is uniform for all, and all the space data in most of the cases, whatever kind of data you will be needed, is available on public domain. Maybe you don't know the sites, maybe you don't know the where you can get those things. I am going to introduce you with few of these kind of sites, and keep going through those sites, and you can get more 50 more that kind of links that you can get content from, right? So these are different domains that you can actually participate with the social media marketing skills. On the other hand, if you're a creative person, right, so if you're a video editor, if you're a photo editor, so you can actually use those skills to participate into different kind of hackathons. Like we are having NASA Space App Challenge, that's our international hackathon, and we are the organizer of that thing. So in that particular hackathon, we are allowing people to participate with their creative fields as well. You can build a presentation itself, and that can be applicable to be participated in that event. And there are several this kind of events done by NASA, ISRO, and different space agencies, right? What you need to do, you need to build a network with them. How? Go to every social media, go to every pages of NASA, ISRO, ESA, that is European Space Agency, Japan Space Agency, go to their all pages, all profiles, and start following them. So whenever you are getting back to your social media, because that's addiction, I cannot change it in one day. So what I can do, I can give you certain tips and tricks that can be helpful to use your addiction in a very positive way, that can really help you to learn and get networked with the domain you love to do. So it's not only with the space, it's an example, because this is a space session. If you want to do it in robotics, IoT, everywhere you can actually do, you can actually go. So the thing is, you have to stay with that kind of people who is in looks in the way that you want to be looked after 10 years, right? So in that manner, in all social medias, in all your profiles, in Instagram, everywhere, you should like those people, those pages, those companies, those organizations that can really help you to grow and build a career around it, right? Because it's a very strong medium. Suppose every time you are going to Instagram, suppose you go 7 times to Instagram, like 10 to 15 minutes span every time, right? So if this time, every time you are scrolling and you are getting 1, 2, 3, 4 space related newses and events and webinars and hackathon newses and all those kind of stuff, see how much you will develop inherently, unconsciously. You are not actually going to a blog and reading certain content, you are just spending your time in social media, but still your brain is learning continuously. That's how you can become a self learner, right? And that's a very negative point for my business, because I take money to teach people, but still I want you guys to, all my students, to become self learner, because if you become self learner, we can togetherly research rather than only teaching you, right? So that's why I try to focus on the self learning pattern, how you can actually self learn about the space or any domain you want to do, right? So this social media is very strong medium. So just do it for one week and come to me and say me, if there is no progress, if there is no change in your life, then come to me and say. Just try it for 7 days and you can see the magic, how the law of attraction. So you will start thinking about space, and the space is coming to your phone, your eyes, your brain. And after a certain time, you will see that you will think of participating in a hackathon, and you actually got an offer to participate in a hackathon through your Instagram profile. How this happens? This happens through neural marketing, and I will let you understand what is neural marketing in digital media marketing class. But the thing is, you can actually manipulate the social media algorithms in this way, because they are meant to do so. You have to make a network with the people you really actually needed to follow, right? So I have all the NASA pages in my profile, all the astronauts in my profile. I talk to them, and in case of space, in case of this kind of technology, the world is very small place. So you can go to LinkedIn and get connected with the AI researcher of NASA Jet Propulsion Lab. You can get connection with the direct jet propulsion lab, because every time they are saying something, you are hearing, you are listening, because they are from your network, right? So that's very important. Anyways, so let's get into something interesting and see certain things related to Mars, because I love that planet. Because there must be always a second option, right? So plan B needs to be there, and Mars can be a plan B, because plan A couldn't survive forever, because nothing is forever, right? So that's why we are going to get a few details about different Mars missions. We are going to learn about what is deep space network, what is Mars relay network, and all those kind of stuff. And going through this process, we are actually learning now we were in Earth at 4 o'clock today. Now we build a rocket and came to space, right? Now we are going to learn about different planetary systems, then go back again and build a rocket in a hands-on way. So let me just share a few things. Sure. So this is the official site for all the Mars mission that NASA is conducting, right? So this is mars.nasa.gov. I am sending the link over the chat. So for your later use, right? So what we can see. So Curiosity is a rover. So let me explain what is a rover. Rover means it's a autonomous vehicle or semi-autonomous vehicle, right? That actually go to space in different planets and actually hover over there, right? So rover is a ground vehicle, right? That actually uh, into different planets, different spaces to get certain kind of data. Now why we couldn't send people? Because in most of the cases the biological beings are very susceptible to changes in the environment, and a mechanical thing is not. And that pack actually help that actually let us build rovers to actually go to any kind of planets and get scientific data to understand the different aspect of the planet, the climate, the soil quality, whether there's water or not, any biological evidences or not. Why? Because the ultimate goal is one day a biological being can go to that planet, because we try to expand the whole society, right? So we can become an interplanetary species, so we can actually upgrade our species to different planets. uh, so that is a rover. So rover means a vehicle, ground vehicle that can go to other planets, right? uh, let's go to Curiosity. Okay, so anybody know what is Sol? What is Sol? SOL. Anybody? What is Sol? A mixture of different matters. No, it's not chemistry. It's rocket science. So Sol is not that. Anybody else? What is a Sol? Okay. Mixture Martian solar days. Fantastic. So Sol means Martian solar days. Why we are referring as Sol? Because it's a little bit different from the Earth one. Like we are having like 24 hours, not actually, a little bit less or more. So we are having approximately 24 hours as a daytime in Earth, and the Martian is a little bit different. So that's why that's why if we shouldn't mix and match between the days of Earth and the Mars, right? So that's why they have created a different unit to measure the days of the Mars, that is called Sol, right? And here in the sharing screen you can see that they have written this thing: Sol 31243 23125. It means the Curiosity rover is on the Mars from the begin from last 3124 days, right? It's between the 25 and all those kind of stuff. So that's a timeline, that's a time for Mars. Time and location. So this is the real time data of all the rovers actually hovering over in Mars right now. So right now the time and the location of the rover is this. The distance traveled altogether, this one. mission clock. So they have converted the days into sols, and rest of the things are same as Earth, right? Signal status, that whether they are sending signal. So where they are actually sending the signals, can you tell me where up? So how we connect with these particular rovers, how we actually connected to them, how we can communicate with them? Any idea? How we actually communicate with the rovers in Mars? We are having like 5 rovers over there. Yeah, near about 5 or 3. I have to check. Anyway, so we have many rovers in Mars. So how we actually communicate with them from Earth? Anybody? Electromagnetic wave. Okay, wave. Yeah, absolutely wave. There is only one way. Is it radio? Is it radio wave? Okay, yeah, it's radio wave. But I am actually trying to know about the implementation part, that how it's going to happen. Like, are we directly sending the signal to the rover, or how it's happening? Rover connects with Mars satellite. They connect with our satellite. Uh, yeah, to some extent, but those are not called Mars satellite. Yeah, we can call it according to the way they behave, but they are called orbiters, right? So we are having several orbiters, and those orbiters all together, 3 from NASA and 2 from European Space Agency. So these 5 particular satellites, they are actually satellites, but they are called orbiters, and those orbiters actually connect with the rovers over Mars, right? And get the data from the rover to that particular orbiter, and that orbiter send the data to Earth, right? And how these two things happens, just a second. Yeah, orbiter. So let's know about few orbiters, then we will know how these communications are happening. So this is Odyssey. uh, Time in orbit, it's about 19 years in orbit. Signal status, deep space network. So see one thing, they are not using sol, right? They are using uh, years and months and days, right? Not sol. So in case of rovers, we are using sol, but in case of orbiters, we are using days. Why? Can you tell me why? Why we are actually using days for the orbiters but sol for the rovers? Why it's happening? Because they are not in Mars. Absolutely perfect. So they are actually revolving around the Mars, and it's not in Mars. So the sol is applicable to the substances, whether it's a human being, whether it's a machine, whatever kind of thing is, to those things which are in Mars, which is touched the ground, or which is in the close affinity of Mars, right? That is comes under the sol. But in case of orbiter, they are revolving around Mars. That's why they are already using the days, right? Like they're using in Earth. Signal status, receiving. It's only receiving data. Okay, fine. So this is one orbiter. Second orbiter, MRO. So the full form of MRO is Mars Reconnaissance Orbiter, right? It's launched in August 2005, carries the most powerful camera ever flown on a planetary exploration mission for homing in on details on Martian terrain with extraordinary clarity. While previous cameras on other Mars orbiters were able to identify objects no smaller than a dinner table, this camera is able to spot something as small as dinner plate. This capability provides not only an astoundingly detailed view of the geology structure of the Mars, but helps identify obstacles that could jeopardize the safety of future landers and rovers. So, what is the purpose of this orbiter? This orbiter actually have a camera on board, right? Which camera is very powerful to to actually recognize something of this size, a plate size, right? And how these things are actually helping the helping Mars to do different kind of space landing missions. Because if they don't have the NASA people don't have the terrain geographical 3D models of Mars, they couldn't plan where they should land their lander and where the rover that will come out of the lander, and the rover will move around, right? So they have to choose a place which is less hazardous, and if there is a hazard they should have the data about it, right? So how this thing are happening, this particular satellite is capturing images of different part of Mars, right, and sending back to Earth, after processing certain things, sending back to Earth. So from that particular image, through high level of 3D image processing, we can actually understand the depths, the size, and all those kind of stuff from those images, and we can actually build 3D texture of the whole land, whole geography of the Mars. And that is actually helping us to understand where to place the rocket, when to leave, which particular attraction force needs to be there so that it can land on a certain particular position, and which is less hazardous than the other, right? So that's how these particular orbiters help. So another work of orbiter is they actually talk to the rovers that is moving around in Mars, right? And it's a two-way communication. They can talk to the rover can talk to them back, right? So what they talk to rover, they say that the Earth people have tell you to go 10 steps forward. The Earth people have asked you to check whether your battery is okay. The Earth people has asked you to check whether there is a water in the soil or not, right? So to send instructions to the rover from the Earth, we are using certain things called deep space network, right? So it's like a mobile network, that the mobile network actually help us to get connected with our cell phones. And this deep space network is something which is help us to connect to our rovers with the help of the orbiters, right? So there are two particular networking is happening in this communication. The first one, just a second. So Maven is another orbiter. I'm not going to get into details of Maven. So you can just check out in the website, and you can get all the details of those. Just a second. Yeah. So how these communications are actually happening? We are having two networks. One is deep space network. Another one is Mars relay network. And how these two things are happening? We are having giant antennas over here in Earth, lots of giant antennas, right? Those are responsible to communicate with the satellites which we are having in our affinity of Earth, the Earth satellites. Those satellites talk to the orbiter, right, which is actually creating. So there are 5 orbiters, 3 from NASA and 2 from European Space Agency, which is actually forming the Mars relay network, right? Relay means it's repeating the thing, right? So the Mars relay network is connected with the satellite network of Earth, and that satellite network is connected with the radio antennas, huge level of radio antennas in Earth, right? And this particular network is called deep space network, right? And the network, this particular satellites, the orbiters are having with the rover is called the Mars relay network, right? So the communication with the rover is happening through 2 networks. One is sending data from Earth to the Earth satellite, to the satellites as satellites or orbiters in Mars, and those orbiters are actually sending the data to the rover. And that's the reason that it takes around 11 to 12 minutes to send one instruction to Mars. So if you press a button, suppose you are playing with the Mars rover, right? So you have somehow luckily you got the access from NASA that you can actually play with the Perseverance rover with your keyboard, and you just pressed the arrow key. So one arrow key press will go to Mars. It will take 12 minutes. So you can see the rover is moving after 12 minutes. So you have to be very careful. So if you are playing like NFS, that's not going to happen. So it needs to be very planned instructions. And how they're planning the instruction? Because they are actually watching the rovers from the orbiters, right? So where the rover is, what is the 3D geographical terrain over there, and how much it should go forward, backward, and they plan the whole instruction and send it to the rover, and the rover go from that place to that place to that place and stay and do his own work, right? So that's how these things work. So we know about two network. One is deep space network. So it's an interplanetary network to build communication between the planets and the solar system and the beyond, right? So this is called deep space network. And I can just show you a few antennas which used for deep space network. Just a second. Yeah. Yeah. So these are the 5 satellites that forms the Mars relay network. And these are the antennas. These I don't know how much you can understand the vastness of the antenna. It's like football ground, right? It's very huge level of antennas that actually used to do this thing. And yeah, so this is a place, I hope everybody can see. So you can actually play around with the Mars relay network from here, right? You can actually see which satellite is over, which observer is over where, and do several things with them, right? So it's a live real time thing from NASA. And we are all actually building a very interesting thing in Think Again Lab. So we are actually building a full body gesture control system. Anirbal is leading that project, and it is his idea that we are mentoring, and we are building a product out of it. So it's like a 6 sense technology. We are building a full body suit. You can actually get into a VR, and you can control the virtual objects with the bodysuit, right? And it's already working. And all the in the robotic session, we have shown that how we have built the finger sensors and all those kind of stuff. And for so whatever you can see in this particular 3D animation, you can actually see this in virtual world, right? So you can see which particular satellites are actually moving above your head in Earth, right? With the VR AR/VR app, mixed reality apps we have built. So maybe on some other session, if we are having any AR/VR session, we can show you how actually it works, and how we can really see all the satellites in real time, that how it's moving above our head, right? So this is, and just click on, so it will give us every detail about all the landers, right? I have selected this lander. So it is giving us all the details about all the landers, and we can use it. I am just sending the link of this particular site. Yeah. So we have understood what is rover. We have understood what is rover, what is orbiter, how this deep space network, Mars relay network is happening and working all together, right? To let us connect with the rovers in Mars. Let's get into something else. Just let me share the screen again. Yeah. So if we go to the Perseverance site, yes, so we can actually go through all the parts of Perseverance in 3D view and understand what every part is doing, right? So the rover is loading, and we can actually go through all the parts of the rover and understand what every part means. I'm sending you the link for this. See, now we can actually, in 3D view, we can actually see all the parts of this rover. Suppose this one, a multi-mission radioscope thermoelectric generator provides electric power to the rover. So the idea that a rover has batteries, rover is not have batteries like lithium ion battery or something like that. These are actually thermoelectric radioisotope, right? Radioisotopes, right? Which actually powering the whole thing with a uh, very common physics phenomena, that if you actually make one side of a metal very hot and one side of the metal is very cold, then it start producing electricity. Now if you are actually making the heat with thermal radioisotopes, it's absolutely at different level, and that's why it can produce a lots of energy, right? So that's how the whole energy kind of thing works in rovers and satellites. Next is, so these are wheels. The wheels are made of aluminum with cleats for traction and curved titanium spokes for springy support. So these spokes are actually built out of titaniums, right? So it looks like very common thing that it's the rover that looks like the rover I built in my tech fest, right? But it's not the same. So the components, the research about this rovers are just outstanding, right? So the spoke are built upon titanium because it's very rigid metal. Next is body. The rover body carries and protects a computer electronic instrument, so we all know about this. And from the learn mode, for every part you can actually get into the details and learn about all the parts of the thing, right? Sherlock. So Sherlock provides fine scale imaging and detect organic compounds and potential biosignatures, right? So it's like a camera, right? Next is arm. The arm helps scientists get up close and personal with Martian rocks and soil, right? So these are like getting the things from the so it's look like a robotic tech fest car with ultrasonic sensors, right? But these are not. These are very high efficient things. But it looks like the same. But the thing is, the logics that we use in different kind of robotics thing in our college fest or in our projects, that actually used in this kind of things, right? So the logic will be remain same, the components will be changed, and that's how you can actually scale up your projects. So these are cameras front. So these hazard avoidance cameras aid in driving, can operate autonomously and avoid obstacles. So these are actually working like a ultrasonic sensor to avoid obstacles, but these are cameras and they are using the image processing on board to detect about any hazard, any downfall in the land or anything like that, any obstacles, and avoid those things, right? So it's a very common project we do when we start building robotics projects. Like we just fit up our mobile phone, get the feed on a Raspberry Pi or anywhere, and try to process the image. So that the same logic, but with higher efficient algorithms and all the hardware components, right? Next is this supercam. Supercam identifies the chemical composition of rocks and soil from distance. So it is a infrared camera which is actually helps to get information about chemical compositions of things with images, right? So it's using infrared and image processing to actually get those kind of data. Moreover, we have completed several parts. There are many other parts, you can get into those things. I'm just showing you the places from where you can actually become knowledgeable about space, you can become influencer of space, you can actually learn about space, right, from the people who are actually doing it. Okay. So you can get all kind of space. So if you want to learn anything about these things, you can get all the details from these places, right? Next, I will show you something. Okay. I was talking about Deep Space Network. So this is the site of Deep Space Network of NASA. It looks like very sci-fi thing like koi mil gaya, but it's very scientific place from where you can know about all these radio places. Like if you click on it, you'll get data of this thing. So we can get all the data, right? View world map, view spacecraft which they are communicating with. So this is actually communicating with Mars ODC, right? That is the orbiter for Mars, one of the orbiter for Mars. So this one is Advanced Composition Explorer, right? So DSA, Deep Space Network, and you can get all the details about all these space networks from here. I'm just sending a link. So this is where NASA, this is a jet propulsion laboratory lab where they see all the communications. It's very fascinating workplace to see. Uh, Anyways, so let's get back to the rocket part. Yeah. So more or less we have learned about the rovers, the orbiters, the deep space network, and all the resources that we can actually get and which can actually help us to get different kind of interesting tools and all those kind of stuff that can help us to understand how things are happening. Right now we are actually going to build a rocket, and if we get time at the end I will show more links, because I have thousands of this kind of links that can just blow your mind from simulators. I will give you a ISS docking simulator where you are actually driving a spacecraft to dock it to the International Space Station built by SpaceX. It's absolutely real-time data feeded, right? So I will just describe about that thing after we have built the rocket and launch it, right? So let's get back to the interesting part of rocket building. So we are not only writing on the posters that you are building rocket, but you are actually going to build a rocket and see how all the things that we have taught in the theories are really going to be get implemented. So on it one, get started. Your visuals are a little bit bloody. Your voice is also not appropriate. Just check your network, I hope. Your voice is breaking. There is a network issue, I think. It's noisy, very noisy. Is it raining over there?
It is raining and also I have a fan over it, so that either of
Can
those.
you just switch off the fan? Your voice is not coming. So what other people are seeing at this point of time in the slide, so that's not a slide, that's a software, and the thing you can see in the image, that's the space, that's actually a space ground station from where we are going to build the rocket and launch it. And it's you can see obviously it's just beside us ocean, so that you can launch the rocket. So this simulator is outstanding out of the world, and you can actually build rockets. Like we are building the Mars rocket actually in the way NASA is building it, because we have all the components in the simulation that NASA is using over there. No, voice is breaking. Okay, do one thing. Let's start the thing. If the voice is not making a problem, the visuals are okay, and is it's going fine, then you can go ahead like this. Otherwise, you can stop the other software, recording softwares, and you can just put the thing on screen share. Your voice is not coming. Your voice is not coming.
Okay, so before getting into the software, I guess we need to learn a little bit about staging. So now what is staging? Staging is basically adding different parts to our product. Okay, so for the experiment, imagine that this is a rocket. So this is a whole rocket, and this is in the bottom is the engine, and the top of the rocket is the payload. Okay, so let's say this thing is completely filled with fuel, and we just launch it and it goes upwards, right? Now the thing is, when the fuel like gets almost empty, so there is a takes very little suction, but it is way because a lot of this thing
Sound not clear. Honorable, sound is not happening. Honorable, it's not audible. Honorable, it's not audible.
Okay. So now is it audible?
Not really. It's audible, but it's not clear. Your voice is not clear.
Still not clear.
No, I hope there is a problem with your mic headphone or the network, audio network. I don't know. Okay, still you figure out if it's not getting figured out. না এখনো ঠিক না, এখনো মানে it's blurry, very blurry, and your video has been paused. Yeah, you check on it. I am continuing with the other parts. Okay, just a second. Yeah. Yeah, so we are checking on this side. So from here you can actually get all kind of data related to Mars. So you can see that SOL 3039. So we are calculating the SOL from the day Curiosity touched the Mars, right? Because that day a particular program has been started, and that is the beginning of the SOL. So they are counting the day over there. MSL means Mars Science Lab, and today's weather in Mars, right? In Fahrenheit, in real time, you can get over here. Today's weather, sunrise, sunset, atmosphere, season, pressure. So that's how actually you can be acquainted yourself with space. So this NASA is actually building so many initiatives, through so many web apps and hackathons and different kind of programs. You can actually be part of all those things and actually get acquainted with all this kind of informations. Like, this is a comparison between Mars and Earth, right? Distance from sun, deepest canyon, diameter, length of day. So this is the difference between the length of day of Mars and Earth. So this is SOL and this is day, right? So day is nothing but a unit, right? Fine. So here we have few apps. I am letting you go through these apps. These are few are very funny, few are very interesting, right? So the first one is send your name. So many people, because of the social media right now, know about this thing, but those people who don't know, I am just going through it so that they can understand about it. So this is a very good initiative of NASA, through which you can actually send your name with different spacecraft that is going to Mars, right? So you can actually put all your details over here and send my name to Mars. Click on the send my name to Mars, and your name will be registered and you will get a boarding pass. I got several boarding passes for that stuff, and they actually write your names on a particular document and send it with the rover to Mars, right? So you guys can check this thing. It's a very interesting thing. It's not a educative, but it's a interesting and inspiring thing. I'm just sending the link over here. One. Yeah, raw images. So from here you can get all raw images from Mars. These are the raw images sent from different rovers to us, right? And these are really amazing and interesting to see. Like these are the filters we can use. So they are saying, so we can understand how many cameras they are having. They are having navigation camera left and navigation camera right, so they are having two cameras for navigation. Second, front has cam means the obstacle avoidance cam, right? So they are having two has cams and two rear cams, rear has cam, right? So they are having two front has cam, two rear has cam. So they are having all total 6 cams, and these are different images from them, engineering cameras, and they are having 6 science cameras, right? So these are the different footages that they got from the science camera. So NASA's Mars Perseverance rover acquired with this image using its left Mastcam Z camera. Mastcam Z is a pair of cameras located high on the rover's mast. This is image was acquired on May 23, that the local mean solar time of this one. So this is most probably a biological uh, lab kind of stuff. Everyone, is it okay? Your voice is okay right now?
Am I audible?
Yeah, absolutely.
Okay, fantastic. Literally left the meeting, reset the whole network, and joined again.
It's okay now?
If it's not okay now, then it's gonna be a really big problem because I reset the whole network.
Okay, go ahead. Go ahead.
Okay. So this is basically the simulator that I was talking about. So before going into that, I would like to talk you a little bit about staging. So basically, staging is adding different parts to your rocket. So basically, imagine that you are going straight up into the air, but your tanks are getting empty, right? So, but the load of the empty tank, there is also some weight of the empty tank, right? But it's getting adding up. So it's basically waste load, right? So why are you carrying around an empty tank when it's empty? But you cannot just drop an empty tank because the engine is attached to a tank. So what do? You build like multiple engine and tank blocks, and then you attach them one by one. Okay. Same thing we have done here. It's called staging. Okay. So right now, this is the first stage. Okay? This is the first stage. As you can see, there is a black part marking the first stage. So this is usually responsible for putting the rocket off the ground. Okay. Newton's first law of momentum. Newton's first law of motion. Whatever object stays in motion tends to stay in motion, and whatever object stays at rest tends to stay at rest, right? So this is like a 5-ton, 10-ton rocket, and it is at rest, and it needs to go upwards against gravity and also against Newton's first law. So from rest it needs to go into motion. So it needs a huge thrust, right? So for that purpose, we use solid booster rockets. Now, what's the advantage of that? It has high specific thrust, right? So you get a lot of thrust, and also there is no availability of steering, but there is no problem because it will only help us to get off the ground. Okay. Now, as you can see, this is a very small. Okay, this is a very small portion of the whole rocket. Okay, like it's like 30%. So after getting off the ground to a considerable height, say around 10,000 feet, the work of this rocket is done. So what does we do? We simply disconnect it like this and drop it. Okay. Now we are left with two stages. Okay. So this now is the liquid fueled stage, and this has thrust vectoring and all other steering mechanisms to help the rocket guide the rocket to the upper stratosphere. Okay. When we exit the stratosphere, when we exit the troposphere with the terminal velocity, there is like very less gravity over there, and so there is no need for this heavy rocket, this heavy part of the rocket to be around, because it will only act as a force of pulling it down to earth, right? So what do again? We disconnect this part and drop it in the stratosphere. Okay. So as the other part fall into the ocean immediately, it does not fall immediately, but it stays in the stratosphere. But eventually, it falls down and burns down during the re-entry. Okay, so it burned down. So only we are left with this part. Okay, now this is basically the payload carrying stage. It only has a small booster, a very small booster, and a satellite carrying stage. Okay, or a payload carrying stage. In our case, this is basically a satellite. So it goes into the orbit. It launches the satellite, and its job is done. So it keeps floating in the orbit, and the satellite gets into the orbit. So now the question is, what happens to this upper stage? Because it goes into the orbit, it stays in the same orbit as the satellite. So this is where the problem of space junk comes in. Since we have done so many launches, so many satellite carryings to the Earth's orbit, to the Mars orbit, to the ISS, a lot of this upper stage debris and other debris that from the Apollo missions, the missions that went to the moon, all that space junk is getting accumulated slowly around the Earth's orbit, filling it up. So, what is the danger of that? Well, firstly, it could crash with any rockets incoming back, like coming back from the space station. Secondly, it could also crash with other satellites, making these billion-dollar devices go worthless in a blink of an eye. So for that purpose, they are like progressively getting more and more hackathons and more challenges based on space junk clearing devices. Even the European Space Agency is even developing a kind of a laser mounted on a satellite. That satellite will be only responsible for clearing space debris by hitting them with a laser so that they can change their trajectory and put them in a trajectory where it can burn up on re-entry. So this is basically a big problem of space jump. Okay, and this is how we do staging. So with staging out of the way, let's jump into this simulator. Okay. Now this simulator is a very heavy software, like fair warning. So if you don't have a very highly beefed up system or even a medium system, you won't be able to run it. I have a fairly medium system, and even running it on low specs, low settings, it still puts a lot of pressure on my PC. As a result of which, you guys saw a little bit earlier that my voice was breaking up, my video was breaking up as a result of that only. So I will be going into the simulator. So before I go into the simulator, I just need to check one thing. Is my audio and video is clear, right? There is no problem right now, right?
Audio is more or less clear, but there is an issue with the video. It's flickering. I hope for network you can check on it. But I am afraid that whether it's it don't crash your voice.
Okay, is the video okay now? Is the video okay now?
Yeah, video is okay.
Yes, absolutely.
Okay. So let's get into the simulator. So this is like a whole spaceport. Okay. So we have buildings, like different kind of buildings. So if I move out of the way here, so if you can see, that's a vehicle assembly building. So the writing is very small. I don't think you guys can read. So it's a vehicle assembly building. So this is where the rockets get built. Okay. Next up is the space plane development. Oh, it's flickering again. Okay, so basically it's flickering due to the pressure on my system. Sorry, really, I can't get this. So it's like a very heavy software. So because it simulates real life physics and all of the whole Earth terrain and the moon and the space around Earth, including but not limited to Mars and other exoplanets. So for that purpose, it's like very heavy simulation, and for that purpose, my system is a bit overburdened and it's flickering. That's why. Okay, guys. So this is a space plane building hangar. So what's difference between a space plane and a vehicle assembly? So launch vehicle, as has been previously described, the rockets that goes straight up into space. While space plane take a gradual approach, and go, like either they are dropped from a supersonic plane and they get some assisted launch and they go right through the stratosphere into the space, or they get into space with other launch vehicles, assisted by other launch vehicles. So whatever I said, the examples of those are: number one, if you are talking about assisted by a other launch vehicle, it's very simple. It's a space shuttle. So the space shuttle was a space plane by itself, but it got assisted by boosters and other big rockets to jump into space and then land by itself. Okay, and then the other thing that was assisted by a plane, this was a NASA project called X5. It was a supersonic rocket in the early 90s, or sorry, maybe in the early 80s. So 1980s. So it would be dropped from a Boeing 737, like modified by NASA, and it will just take off mid-air and go straight up into the space. So that's why the space plane hangar is there. So right now we will be building rockets. So let's go into the vehicle assembly building. So this is basically our workspace. So these are the like different parts, and this is basically the area where we will be building the rocket. Okay. So let me build a very simple rocket. Okay. So the first thing I will take will be a command pod. Okay. This is where our astronauts will be sitting inside. Okay. As you can see, I have got a command pod. Okay. Right there. So there is a command pod right there. Then, like when, as I said, when we don't need the stages, we disengage them, right? So for that purpose, I'm going to be using something called a decoupler. So there they are, a decoupler. I will be using a S18. So I will be using a TS18 decoupler. You keep experimenting on this thing, you guys will get like what decoupler to use in which situation or something. So the cockpit of the pilots is done now. So we will move over to the fuel tanks, because of course we need to carry fuel, right? So I'm gonna add some fuel tanks here. So I'm gonna add some T400 fuel tanks. So the model number of the fuel tank is T400. So fuel tanks are done. Now let's go for the engine. I'm going to be using this P45 liquid propelled swivel engine. Okay. Done, as you guys can see. Now let's think a bit forward, right? So the rocket goes into space. Okay. Now it has to come back to Earth. What will it use to decelerate? Parachute? Have we installed it? No. So let's install it. Let's get a Mark 60 parachute. Once again, there are many different kinds of parachutes. You guys keep experimenting on this thing. You guys will eventually figure out what to use in which situation. Okay, so now technically our rocket is built. Okay, technically our rocket is ready, but it's not still aerodynamically stable. So what do we need for that purpose? Fins. So I'm gonna go ahead and I'm gonna take some fins. So as you guys can see, these are the delta fins. So I will be using this only. Now, to increase the number of the material, I will just click here. So I will add three pins like so. So as you guys can see, our rocket is now basically ready. So this is a very basic subsonic rocket designed to build, designed to go up only to the stratosphere and no further than that. So one additional feature that I would like to add is a heat shield. Okay, so I will remove this thing and I will add a heat shield. So, if we shield added, now I will add the rest of the stuff here, and it's done. So this is a very basic launch delivery vehicle. It will only go to the space for a few moments, and then it will come back to Earth. So let's launch it. Give it a bit of time. Heavy application. Okay, so we are on the launch pad finally. So there is our little rocket on the launch pad. I will zoom in on it. There we are. Yeah. Now let's focus a bit on the UI here, okay? Because it's very important. Up over here is the altimeter. So the thing you see, the square thing with the numbers in an M written after it, this is basically the altimeter showing that how high we are going. Okay. Uh, this on the bottom. This is basically our orientation guide. Okay. So this shows the horizon. So we are pointed towards the top. So this is calibrated to the top horizon, and then we can change it as we go. And whenever we change the direction of the rocket, it will denote what direction we are going in and where the ground is. So it's the same tech used on aeroplane to keep it in ground. So next up is the speedometer. So this is basically measures how what is the acceleration of the rocket and how fast we are going in meter per second. Okay, so that's the altimeter and that's the speedometer, not to be confused. That measures the altitude of the rocket from the ground level, and this measures the speed of the rocket, the acceleration of the rocket in meter per second. Okay. Now I'm going to turn the SAS. So SAS is basically computer assisted driving. So it's basically a gyroscope that is built into the rocket, and whenever you try to turn the rocket, the gyroscope will talk to the engine through a PID control loop, and that will accurately control the rocket more accurately than a human can possibly. Okay. Let's hit space and see what happens. Okay, nothing happened. Why didn't anything happen? Because obviously the throttle, see the throttle is at 0. It did not even start the engine. Let's do that. See, as soon as I started the throttle, started going up. So there is our spaceport. So you guys can see there is a horizon. We are going up, and this is all happening in real time. Okay. So this is our kilometer gauge. We are going straight up. Means move side. As you guys can see, we are going full throttle and up at full speed. Okay, so right now we are 2000 meters. Not much, but we will keep going up. Now we are at 3000 meters, and as you can see, the air pressure, the wind pressure, it's visible because as we go more and more higher and higher, the air gets thinner and the air friction begins to show. Now we are 10,000 meters, so This is basically the height at which helicopters and small airlines fly. As you can see, our fuel gauge shows that we are almost out of fuel, and since this is a single stage rocket, we probably wouldn't be able to go a lot higher. So now we are at 20,000 meters. So this is a lot of high, like the higher planes that go to the edge of space, they fly at this altitude, and as you can see, we are going out through the stratosphere. Okay, we are going out through the stratosphere. We are out of fuel, but we are still going up considerably because we have gained that momentum, and now the gravity is pretty thin and the air pressure is pretty thin. So we are going. We are shooting straight up towards space. So as you guys can see, previously it was a blue sky, but now, right now, the sky begins to go blacker. Okay? Because we are reaching the edge of space, and if you guys can see, there is the surface of the Earth. Right there, you can see in the background, there is just right here is the moon, and then beyond that is the Milky Way. Just beyond that, and since that is the moon, on the exact opposite side will be the sun, right there. Okay? So basically, this is how the sun reflects the light of the moon. So there is the moon, there is the sun, and there is the earth. So basically, the moon is reflecting the light of the sun that far end of the earth. Now we are at 70,000 meters. So we have finally reached the edge of space, as to say. Okay. So now we don't need this lower stage. We do not need this lower stage to work with anymore. So I am gonna just decouple this lower stage. As you can see, that lower stage is gonna fall down to earth into the sea, and now we are just left with that command module. Okay. If I zoom in, you guys will be able to see. So this is the command module. Now we are only left with the command module. Okay. Now if I press M on my keyboard, this is a map, and this is where we are exactly right now. Okay. So this is where our airfield is. So this is where we took off from, and this is our trajectory. See this AP? This AP means apogee. Apogee is basically a technical term for the highest point that we are going to reach. For Earth's gravity, for our velocity becomes zero, and Earth's gravity pulls us back into the Earth. Okay? So this is basically gravity-assisted flying. So as you guys can see, we are almost reaching the apogee, which means this is the highest point that we are at currently. And after that, the Earth's gravity will do its job, and it's gonna pull us down back to Earth. Okay. Now this is a very boring stuff, like the most boring stuff of space is waiting. Fortunately, we have got something called time warp, which means we can slightly bend the rule of physics and accelerate time itself. What that will do is it will help us. See, I made time 4 times. Now it will help us a lot faster. If I open a map, you guys can see we are falling very fast. Here we are. As you guys can see, I have pointed the heat shield directly towards the ground. Okay. So now I will end the time warp because it's time to open the parachutes. So as you can see, we are at 8,000 meters, 9,000 meters right now, and we are falling. And the parachutes usually open at 1,000 or 1,500 meters. So let's wait for that timing. So as soon as it hits 5,000 meters, I'm gonna hit the parachute. Okay, why I'm gonna hit the parachute? So that it deploys. But if you guys can see, it will not totally deploy. It will deploy in a deflattened state. Why? Because once again, there is no air pressure that high above the ground to make the parachute actually work. Right? A parachute basically decelerates by increasing the surface area and gathering more air pressure. So since there is no air pressure at all, the parachute is not extending at all. So now as you guys can see, since we are below 1,000 meters, the parachute fully extended. like a normal parachute does. And now our speed has been decreased to only 6 meters per second. That is like really slow. That is like the speed of walking, 6 meters per second, or maybe running. So we are very slowly approaching the ground. If you guys can see the altimeter, I don't know if you guys can read it or not, but it's now reading 410 meters. So we are like very near the ground and approaching the ground at a very slow pace of 6 meters per second. Waiting, 17, almost there, and there, hit the ground. So we have landed in a hilly region which is around 200 meters above the sea level. So that's why we landed so quickly. So now, right now, as you guys can see, we are on the ground here. Okay? We are on the ground here, and we have safely got into the ground. Now we can take out the astronauts for a walk around, but we are not going to do that in this one because already staying in the system here. So what I'm going to do here is recover vessel. So this will mean that the guys will get here and recover this astronaut. Here's some wait a moment. See, the astronaut was successfully recovered and he is ready for next assignment. Fantastic. Now let me show you something that I have been working on that's a little recent. Okay? Let me load up the workstation again. Now this was our old rocket that we were using. Okay. Let me go to open. So this will give me a catalog of the rockets I have been working on. Okay. So now let me find the rocket I was using. That's what it's a little big project. Like the ultimate level of complicated. So it will take some time. A moment. Okay, here it is. So if you guys can see, there are like infinite number of stages. It will take some time. It's like so big that I cannot even show you guys it in one go. So this is basically the Mars 2020 rocket. Okay, it's powered by a Saturn V, and it has even perseverance and the ingenuity built into it. So let's draw some comparisons from the direct NASA website. So let's go here. Yeah. So this is the first stage of the NASA Mars 2020, the Atlas rocket. Okay? The Atlas 5 rocket. Okay? So you guys are seeing the visuals. Okay, seen it? Now let's go to our project. Let's focus on the rocket itself. Now let's see what's inside. See? That is the same Atlas 5 rockets with two stages. This was the bottom solid state booster. There is a decoupler in between, and this is the liquid stable state. Okay. Next up is side boosters. So again, the NASA website. So Atlas 5 we have got it. Next is the side boosters of the solid rocket motors. So as you guys can see, this is the Atlas 5 541 motors, the solid rocket ones. So there are 4 of these on the NASA Mars 2020. Okay, and this is how they look. Okay, have a good look. Now, if I project again, see, that's the solid fuel rocket, and once again there are 2 on this side and the 2 on the other side. So there are 4 of them. Looks similar. They are literally built eye to eye with the same parts. And finally, our payload. Right here. Okay. This is a So you guys have seen the sky crane, right? This is the device that drops the Perseverance into the Mars atmosphere. So this is how it looks. Okay? This is how it looks, and then this is the sky crane. Similar. Look from beneath. Side. Okay. So this is basically an exact inside the sky crane we have the Perseverance. This is basically an exact copy of the Mars 2020 rocket, and we are going to be launching it from this simulator only. So if I go to the map view, loading. So basically, it's the whole simulation is like the real thing. Like we are simulating Mars 2020 launch and the landing of the uh, Perseverance and the flight of the Ingenuity. We will be like simulating all of this. So right now we are outside the building. So if I launch into the so we are not going to launch the vessel or anything. We are going to launch pad to get the map view. whole like the space routes from where we have to go to the Mars. So if I zoom out enough, there is our Earth. I hope you guys can see there is Mars. Okay, for copyright reasons in the game it's called Mars, but basically it's Mars. So basically we have to go from Earth to Mars. So since everything is a copy of real life, so if you guys see at the Martian and the Earth orbit, so you guys see how these things are like not like exactly aligned. Guys, if you see from the top. So the Earth's orbit is elliptical and the Mars orbit is elliptical as well. So it means that when the two come closest, like when the Mars is like right here, parallel to Earth, only at that point we can launch a rocket and it will take the shortest period of time. Okay, so that is why like people cannot like launch Mars mission every day or every year even. Okay, so every 2 years there is a window of like 27 days or something like that when like 22 days probably. So in those 22 days only we can launch the Mars vehicle so that it can reach the Mars in the shortest amount of time, and that shortest amount of time is also 8 months, so not so short. So basically, in total, going to Mars. So if you decide to go to Mars, then even if you have a fully capable rocket, and even if you are fully trained, it will take you at least 2 years and 8 months to get to Mars. So that's why the process of sending the rovers are slow as well. Okay. So this was basically the software. So if you guys want, you guys can download this as well. Also, there is like a smartphone version of this as well, but the graphics are not so good, but it's lightweight. Okay, so now since we have time, we have enough time in our hands, let's check out the application that we have developed. It's called ACE, Augmented Space Eye, because obviously it works in AR, augmented reality, and it's based on a space where you can see everything about space. So we named it Augmented Space Eyes, or ACE for short. So let me fire up that on my smartphone, and I have to connect that to my computer as well, so for you guys to see it. So Arjita, would you like to take over with some more Mars links and stuff like that?
So you are preparing the app, right?
Yeah, I'm going to connect my phone because I'm using the phone as my camera. So I will.
Okay, fine. Till then, I will just show the simulators and different kind of things.
Sure.
Fine. The first one. So how many of you know the name of SpaceX? How many of you know about SpaceX? What is SpaceX? What is SpaceX? Anybody? A space delivery company, a space company, space research and development company, owned by Elon Musk. And that SpaceX company, yeah, Elon Musk, not double L, it's a single L. Owned by Elon Musk, which produces spacecrafts. Exactly. So that SpaceX have built a simulator. Simulator of what? So what happens? So when we are actually sending a payload, a cargo, a docker, a small payload delivery system on top of a rocket to the ISS. After reaching very close to the ISS, when the rocket is leaving that particular docker, it will just need to go and dock to the International Space Station, right? And it's an automatic and manual both process, and it takes a lots of patience to do it. So what SpaceX has been done, the particular site that I am showing. So this simulator will familiarize you with the controls of the actual interface used by NASA astronauts to manually pilot the SpaceX Dragon 2 vehicle to the International Space Station. Successfully docking is achieved when all green numbers in the center of the interface are below 0.2. Movement in space is slow and requires patience and precision. So if you really play this game, you can understand why they are again and again saying about patience. I am sending you the link and showing you the game a little bit, not the whole game, yeah, a little bit amount of it. Is the link of it. So this is the control, and you need to control it. It requires a absolutely accurate level of control, and all the numbers need to be absolutely perfect. And we have to point to this green point. So when you see a flashing of white light on the keys, it means we are actually controlling the thing manually to dock to the ISS, and the vehicle you see in front of us, that is ISS, International Space Station. So it's a place where astronauts go and live for weeks or months or years to actually do research about space. And it's an outstanding phenomena, kind of innovation of human beings to build this kind of ISS where people can go and live in outer space. So actually right now I'm not playing, but if you want, you can go and actually play this game. It will develop your idea about how actually this space is so much of patience is needed, and how actually it happens, like docking. What is the docking? So docking means the vehicle is going to get attached in a particular hatch of the ISS, because if it's not getting attached, they cannot be synchronized, right? That's why. Okay, so this is the ISS space. Next I am going to just show you a 3D video, though it cannot be 3D in screen sharing, but still you can get a visual that will. So this is a 3D virtual tour of International Space Station, right?
Okay, I'm good to go. After this, yeah, like ISS tool, we can go over to the.
So in ISS, we are having different kind of cabins and different places for different countries, right? They send their astronauts and they stay over there. So it's like a small version of the world with very limited resources to do the scientific experiments. This is how they need to gym to just keep the body strength, because there is no gravity is working, so that's why there is a problem of limbs. This is how the Earth look like from ISS at different points. This this is done by European Space Agency. Like we are having NASA for USA, ISRO for India, so we are having European Space Agency for Europe, right? Next, I'm going to show you certain simulators from NASA. Before that, I'm just going to give you a Aladdin's what do I say, the khazana kind of stuff, right? This is called eyes.nasa.gov. From here, you can get several kind of simulators and different 3D animators and all those kind of stuff to understand our planetary system, the Earth, different satellites, exoplanets. It means the planetary systems outside of solar system and different places, different Milky Way like constellations and all those kind of stuff, right? With 3D animations and 3D real-time view. I'm just showing you those things. So this is the place where you can get all these kind of things. So I'm going to show you 2, 3, 4, 5 according to the time, and rest of the things you can go by yourself and check. I'm just giving you the link for it. I have a very okay. Somebody have a question. I will answer after giving the link. There is an option of gravity. Okay, fine. I have a very basic and funny question. How do you the we get oxygen, there is a space station. How do you feature of gravity and gravity of? I didn't get your questions. If I get time at the end, I will just describe those things. Okay, somebody only one has replied. Funny, fine. So let's experience one of them at first. That is exoplanet live view. This is exoplanet live view. Just what happened? A little bit time to be loaded. Yeah. So what is this? Just let me. On average, it is estimated that there is at least one planet for every star in the galaxy. That means there's something on the order of billions of planets in our galaxy alone. Many in Earth size range. These planets outside of our solar system are known as exoplanets. Highlighted stars are known to be have exoplanets orbiting them. Once you click the exploration now button, okay, fine. So let's go and show you. Suppose I am clicking on this. So this is some other galaxy or star, right? So we reached over there. So you can actually go to exoplanets through this 3D visual simulator, and you can just experiment with these things. Even if you click, you can get different kind of informations here. So what is this? What is different kind of parameters about this thing, and how actually it will take you to reach those places. So if your travel speed is 60 miles per hour, so you will reach in 14 billion years to that particular place. If your speed is light, so 1000 years. If you are going in light speed, you can reach that place in 1000 years, right? This is the planet, a Neptune like gas giant planet. The name is this one. So if you want to remember and memorize, if you can, but I don't want to, right? Anyways, so this is a star, a G type star, which is not visible from Earth, right? And it's the distance from the Earth 1239 light years. So the point is, you can actually visit this site and actually go through all the exoplanets we got from all the different kind of data and telescopes and all those places, right? So this is one. Next one is Earth, right? Just a second. Yeah. Loading up. Yeah. So this is a 3D visual simulator of Earth, and all these things that's revolving around Earth are the artificial satellites. So you can actually click on them, you can know about them, you can see them, right, in real time. This one, this one, right? So in this way, you can actually get all the details about all these kind of satellites that is actually moving around Earth.
Arjita, the app is ready.
Okay, okay, fine. So this is another one. I'm just sending you the link. Yeah. And there is a very interesting thing. I'm just showing you the last one. Then we'll get back to the app. Okay. Yeah. So we can actually see the pre-landing simulation of Perseverance rover from this kind of app. So we know that last year Perseverance went to Mars, and this is a simulation of that thing. You can see the whole timeline from the orbit to the ground, right? And we can just actually make it speed up because we don't have that much time, so they can see how thing happened. See, so it's 1 minute per second speed. It took, in reality it took many more time. So this is the heat shield is burning and it's going to the place. So that is a rover, and that's just got to the crater. This is the rover, right? Yeah. So this is the Mars surface, and it landed over there, right? I'm sending the link for this one as well. Yeah. So everyone, go ahead with the app thing, and we can conclude over that as well.
Okay.
Yeah.
Arijita, can you just stop sharing the screen so that I can take over? So this is basically the UI of the app mirrored over to my uh, PC. So these are the options that we put in the app. Like this is still in alpha, so we are still basically adding features. And since this is in augmented reality and virtual reality combined, mixed reality really, so I will turn my camera as well, so that you guys can see how I'm doing this. So this is my phone mounted on a tripod that I will be using as a virtual head. So when I move this thing around, that application will work. Okay. So now let's start with the spaceport map. So as the name suggests, this is basically a map of all the spaceports around Earth. So as you can see, it's totally in augmented reality. So it's like literally looking at my room here. So that's my green screen and there's my microphone. As you can see, it's totally overlaid on the room surface. And see this tiny little marks on the earth. Click on one of them and you guys will be able to see this whatever the spaceport you have clicked on. So these tiny marks are basically all small spaceports. Okay. So next, let's go for the satellite map. So basically, satellite map is same as the spaceport map, but for the satellites. So there are like thousands of satellites around Earth, right, at the moment. So we have taken something around 40 to 50 satellites, and we have given them an AR fill. So once again, click on any satellite. This will give you the apogee, the perigee, which is the farthest point and the like the closest point where it is at Earth, what longitude, what latitude it is at. It will also give you the inclination at which the satellite is going, which means that you can figure out the orbit. And all of this information is coming directly from NASA APIs. So this is basically official NASA database that we are pulling the data from. So this is very live, and if say tomorrow this satellite gets decommissioned, so if you click on the satellite, it will show that it's decommissioned. So this particular satellite is a SAT-D. So this is basically a, I think, weather monitoring satellite. Yeah. So it's a weather monitoring satellite that was launched from the Vandenberg Air Force Base on June 2017. That's really new. Let's go back. Got something else. So as you guys can see, the interface is a little rough. So it takes some time to go from one screen to other because as I already said, this project is still in alpha. So yeah, this is a Acme stack. Okay, so it's on a polar orbit, which means that it flies over the North Pole and the South Pole. It runs perpendicular to the rotation of the Earth. So polar orbit. Oh, okay. So it's a radiometer, which means that it measures the native radiation coming out of the Earth. So if say there is suddenly a radiation outburst in some place, it will be able to catch that from space. Now, these are all the satellites that are over the whole Earth, right? So, what about over your head? So, what if you could know that what satellites are right here over your head at the moment? So, yeah, we thought of that as well, and we have developed a system that lets you understand what satellite is exactly over your head at the moment. So, this is the satellite here. Let's get out of this thing. Now let's go to live satellite tracker. So as the name suggests, it tells you what satellite are directly over your head. So satellites usually are in orbits like thousands of meters above the Earth's sea level. So over your head usually means in a broader aspect over the country. So that's what we use. So as you guys can see, there are like two satellites directly over India. So now filling out the details in this small of a screen was a bit of a hassle. So what we did, we printed out the node numbers. So NOARD, So node numbers are like something like, since we're all Indians here, it's something like your Aadhaar card number. So you put that number, you get every single detail about the satellite. Just search satellite NOARD number. This. Like right now, it is like 41460. Just search this number right now. Google it. Satellite node number 41460. It will give you everything there is to know about the satellite. And now, if we want to see exactly at what inclination the satellite is at, just let's go to this advanced mode. There it is. So as you guys can see, it's again have tapped the camera, but this time there is a surprise. So if I move the camera around, should be a satellite somewhere around here. Whereas satellites, these things are usually pretty hard to locate. Okay. So over there somewhere. This is kind of like treasure hunting. You have to move your hands until you get a lock on that satellite. So that is good. Let's try and see. So guys can see both the satellites. Okay. There it is. Okay, they're out of range. They're totally out of range. So that's why it's not showing. So now let's try something called the NASA Research Facility. So here we took one of the NASA space centers. It's like as far as I remember, it's the Vandenberg Space Center. So we found some 3D files of that lying around in internet, like official NASA 3D files of that space center, and we use that as an inspiration to build a fully fledged VR NASA space facility, as you can see here. So we spawn in a room, in a control room, where there are like many equipments and devices, and we can move around. And this is where the suit comes in. Okay, so this is you wear the suit and you
Only one,
use.
your screen is also only showing certain folders.
Oh, okay. That came on. Like, Hold on. This is basically the screen mirroring software. Hold on. Okay, there it is. Maybe the cable got a little bit shaken. So this is basically the you spawn in this room. As you guys can see, this is the research lab. This is one of the rooms of the NASA facility. So let's move around a bit. Now you can control this thing with the suit, but since I don't have the suit right here, it's in the office and it's locked down. So I'm using a virtual keyboard to move around. Okay. So now we have created something of a NASA museum, you can say. So there is the first moon landing, Apollo. Then there is the launch. There is the Gemini. There is the Saturn 5, I believe. Oh no, that's not Saturn 5. That's Boeing SLS. This is a, this is long before Saturn 5. This is a Boeing SLS. There is Neil Armstrong. And then there if you look at this, these are the various rovers. Yeah, that's Curiosity. Building different footprints and stuff like that. Now, if you exit this room, you get transported into the actual full-fledged facility. Hold on. There you go. You spawn on this road. If you look up, so you can see that there are lots of buildings around you, and you were just in this building. So this one you have already seen, and all of these buildings are there for you to explore. So you can go here. So here there is a research going on the astronaut suits and the rovers. So you guys can see everyone is in astronaut suit because they're testing those. Then they're also testing the rovers. We're testing the rover in a simulated environment of Mars. And as you guys can see from my webcam, that all of this is totally like VR. Yeah, that building, if I now next 360. So now, if we go into that building, it says zero G simulator, and since we made this game, we made sure that anything that we put in this game was fully functional. So as you guys might have guessed, the zero G simulator is no exception. So this is a functional bit of tech as well. Code is totally proper. So as you guys can see, there is the zero G simulator. So this basically is actually used for mocking like mock skydiving sessions. Okay, also actually used by NASA actually. That's why I put it here. So this basically gives you a like a fake feeling of zero G by putting a fan below you, like a big fan with a lot of thrust, and essentially pushing you upwards with a cushion of air. let's get out of here. Now we have seen Earth, right? So let's go jump off to another planet. So we put that feature as well. It's called the planetary view. Okay, so Earth we all know. So how about we are talking about Mars, right? How about we actually go to Mars? Okay, so we did bit cheetah wheel here. So we put the Columbia launch footage. Oh no, it's not Columbia, it's Discovery. So we put the Discovery launch footage to the launch sequence. So this is where the actual game begins. Actually, you are in the cockpit of a very futuristic looking spaceship. And since, as I already told you, going to Mars takes around 8 months, right, of continuous travel, and we really didn't wanted a game where you just to spend 8 months doing nothing in the game. So we took a little nifty sci-fi approach, time bomb or spacewalk, we more accurately use scenario. Set, set. And we're ready to go. And there it is. Warp drive. So this will get us to Mars instantly. So the whole 8 month thing like got down to like 2 minutes. So that is this footage is actually of the Curiosity landing. Since we are using the rover models of Curiosity, so we thought it would be good to put the landing footage as well. There it is. Okay, this is where the previous rover differed from the Perseverance. There is a lander coming down to the ground like that. Yeah. In the case of the Perseverance, only Perseverance, all of the rovers before that landed like this. But in case of Perseverance, we use the sky crane that would drop Perseverance and then fly over. So nothing would land like this. Anyway, we are down to the surface of the Mars. And now it's time to roam around because you are right now playing the avatar of Curiosity. Okay. Let's look up. Right now my keyboard has uploaded, but if you guys can see around, this is the full Martian environment. Okay, there is a moon or sun, and if you guys look around, there is no moon because Mars doesn't have a moon. No satellites, like it has artificial satellites sent by us, but no natural satellites. So these blue markers you guys see, these are like fun spots that we have built where you can go and the robot will take some soil samples and stuff like that. So that's it. Like similarly, we also have a moon experience, and we are still developing other stuff as well. So that was the app. Hope you guys liked it. We are also building a space debris section where we will talk about the ways of countering space debris. So yeah, that's it. I'll stop sharing now. Rajita, would you like to conclude?
Yeah. So the conclusion is, I hope you have learned few things. You have got interested to learn few things, and hopefully you will pursue this kind of things. Like you can go for a longer period of courses for rocket science or space related domains, or you can get into the data science and use the space data to do something related to space, but in the data science way. uh, in that way, if you need any kind of helps, if you need any kind of things, you can come to Think Again Lab. And on the other hand, if you want to participate in NASA Space Up Challenge, that's a hackathon, that's a global hackathon related to space, where you can implement your drawing knowledge, photography knowledge, robotics knowledge, IoT knowledge, in any kind of knowledge to solve problems related to space. Another thing is, we are the Network Institute of IISR ISRO. So if you want to do space related courses free of cost from ISRO, and you will get the original certificate from ISRO, and there will be ISRO scientists who will be taking the classes on different kind of technology related to space directly from ISRO. You can just contact us. We can actually help you with getting enrolled over there and get the certificates and do the courses. These are the things. If you We are having like 4 minutes. I don't know if anybody have any questions, they can ask directly. Can I use the software on Win 8, and how can I get those material, please? Okay. Only there are a few questions. You can answer those questions. It's not about share. You can just mail us in the ISRO in hello@thinkagainlab.com that you want to do the ISRO course, and our team will just get in touch with you and let you help you to do the registration process free of cost, and you can learn different kind of technological things from ISRO. And about the software issue, you can go and learn about KSP software. I hope it will be working on Win 8, but the software is very high because it's a high-end simulation. And if you don't have proper kind of facility, like proper kind of infrastructure at your end, then it will be very difficult to run that software because it's a very heavy software. And there is another software which is not this much interesting, but you can still do the basic level of rocket science things. That is open rocket simulator. You can go and download. That's a very lightweight software. You can build rockets and simulate different kind of things, and you can get the numbers. In the end, was rocket science really that difficult? Yeah. So the last question is: rocket science really that difficult? Whatever small amount of things we have tried to teach you, have you understood those things? Is it interesting? Do you feel that it is your cup of tea? Just comment yes or no in the comment section. That's the end of this session. We have only 2 minutes in hand. Okay, I'm giving the mail ID hello@. Okay, yes. Let's see what are other people are saying. So fantastic. More or less, we have. Can you say when robotics class will be taken? Robotics has already been taken, and if you want to go for longer classes, you can mail at the same mail ID. Robotics session we have already done on maybe on the second session. We are left with AI, digital media marketing, web designing, app development, all these kind of things. I hope your university can help you to understand the future schedules. Okay. So we are at the end. 7 o'clock. It's 7 o'clock. Thank you so much for your time. We are done, ma'am. Thank you so much.
Thank you, Think Again Lab. We enjoyed a lot. It is a great session.
Thank you, ma'am. It's our pleasure to.